considers the connected vehicles as probe sensors. They have the ability to transmit the speed and also their position or locations. Also, the measurements from stationary sensors and probe sensors are sent to a fault diagnosis component. This component can detect the sensor fault and also send a model reconfiguration signal to reconfigure the traffic flow model in case of sensor fault. With respect to the traffic flow model, since the traffic control strategies are mainly increment 1 kilometer or 2 kilometers upstream to work zone, we mainly focus on the traffic state estimation in that area. Therefore, we partitioned the section between TS1 and TS2 into 2 segments, and the multiple segments can also be applied using our method. The evolution of the traffic density ρ1 and ρ2 is derived using this formula. And because the traffic state of segment 1 and segment 2 can become one of the 5 states, meaning free, meaning both segments are free flow, and the free conjectured upstream, meaning segment 1 is free flow, and the segment 2 is conjectured with a queue propagating upstream, and also the CCU, CCD, and FCD. Take the FF as an example. The evolution of the traffic density can be expressed using this formula here. Meanwhile, the measurement equation can be derived using the measurements from the stationary sensors and the probe sensors. And also a Kalman filter can iteratively update the traffic state using this formula. For now, we can provide an accurate traffic state estimation using this method, but this method is still vulnerable to sensor fault. To deal with the sensor fault, we designed a fault diagnosis components. The following types of sensor fault are considered. Fault 1, only traffic sensor 1 is down, and fault 2, only traffic sensor 2 is down, and fault 3, both sensors are down. Here, a traffic sensor is down, meaning they generate 0 fluence with the presence of vehicles. The process of the fault diagnosis is shown on the right-hand flowchart diagram. So the essential idea is we provide 2 sets of density estimations from the measurements. And then we can calculate the residual between these 2 sets of state estimation or density estimation. By comparing the residual with a pre-selected threshold and also historical residual, we can detect the sensor fault. And also the fault diagnosis can reconfigure the traffic flow model by eliminating the corrupted measurements. So the developed traffic state estimation with the fault diagnosis system was evaluated on a freeway segment in California, US. A work zone was set up from this milestone to that 37.6 milestone in 2016. And the traffic net was calibrated and validated using realistic traffic measurements from California Freeway database. To assess the effectiveness of the design system, the simulation was run for 1 hour with an artificial fault at time step 1400 seconds. The following scenarios: no sensor fault, fault 1, fault 2, fault 3 are tested under low and high connected vehicle market penetration rates. All the results are presented on the low market penetration rates because of the higher penetration rate has better results. So as you can see from these 3 figures, it shows the residual of the density estimation in segment 1 and segment 2. From the second scenario B and scenario D, we can see once the residual exceeds the threshold, which is shown as the dashed line, horizontal dashed line, we can detect the sensor fault and confirm that sensor fault afterwards. And with respect to the no sensor fault scenario, although the residual exceeds the pre-selected threshold, we compare the residual with the historical residual. In this way, we can avoid a false alarm in no sensor fault scenarios. And also, when you see the scenario C, you can see the residual extraction threshold, and then we can detect the sensor fault and confirm the sensor fault. And now we successfully detect the sensor fault, but what about the performance of our system? So the root mean square error of the speed estimation and density estimation are shown in this table. As you can see, overall, an accurate traffic density estimation was achieved under all scenarios. And a funny part is the error of the density estimation in segment 2 is larger than the error in segment 1 with the sensor fault. Why does that happen? This is because there's a big errors in the speed estimation in segment 2. As you can see, the segment 2 have a larger errors. Why is that? Because there's a mixed traffic states in segment 2, meaning inside of segment 2, the part near work zone area can be congested, where the part away from work zone is free flow. Because there is a mixed traffic states, that means there will be more slower vehicles with slower speed, and this generates a biased speed estimation, and it causes this large error. And this large error will be reflected on the density estimation. But overall, the accurate estimation was achieved. So as you can see from the results, the design traffic flow model and the estimation methods can provide accurate traffic state estimation near work zone area, and also the sensor fault diagnosis can successfully detect the different types of sensor fault and maintain the accuracy of the estimation regardless of the sensor fault. So in the future, the effect of these fault diagnosis will be evaluated using a traffic flow control strategy such as variable speed limit or ramp metering. So one day, when you come across a work zone, hope you don't feel as painful once using the system I developed. Thank you.